Hello, welcome. In this short video, let us look at an example illustrating the properties of ROC curve, that is, receiver operating characteristic. Specifically, in the context of detection of a DC level against wide Gaussian noise, we want to look at the dependencies of the ROC curve, that is, the receiver operating characteristics, against properties such as signal to noise ratio and the detection threshold gamma. So consider the problem of detection of DC level. So under null hypothesis, we have the model of the observation x of n is equal to the noise w of n, where n is as usual equal to 0 to n minus 1. Under the alternate hypothesis, x of n is equal to a DC level A plus w of n. So from a previous video, we already know that the probability of false alarm for this problem can be defined as the Q function of gamma dash over square root of sigma square by n, where the likelihood ratio test is L of x is greater than gamma dash, where L of x is the sample mean. 1 by n summation n equal to 0 to n minus 1 x of n. So this is the definition of probability of false alarm for this detection problem. And clearly the probability of detection is given by the Q function at gamma dash minus the DC level A divided by the square root of sigma square over n. So by using the first definition of probability of false alarm, we can actually construct a value for the threshold gamma dash, which is clearly equal to square root of sigma square over n multiplied by inverse Q function at probability of false alarm. So by using this value, the definition of probability of detection, we can write a new expression for probability of detection, which is equal to Q function at square root of sigma square over n multiplied by Q inverse of probability of false alarm minus the DC level A divided by square root of sigma square over n. So this is the new expression for probability of detection, which can be simplified as follows. Probability of detection PD is equal to Q inverse of probability of false alarm, since these two terms cancel each other, and the other term is equal to square root of n times A square over sigma square. This can be rewritten as probability of detection Q of inverse Q function at probability of false alarm minus square root of n times signal to noise ratio S, where S is equal to the SNR equal to A square over sigma square. Clearly A square is the signal power and sigma square is the noise power. So the probability of detection is clearly a function of SNR. Now let us look at the ROC curve corresponding to the different values of SNR. So dependence of receiver operating characteristics on SNR S is SNR. Clearly for signal to noise ratio that is very close to 0, we can clearly see that probability of detection at signal to noise ratio equal to 0 is equal to Q function of Q inverse of probability of false alarm. And we can ignore this term since S is close to 0 or S is equal to 0. So this is equal to probability of false alarm. That means at 0 signal to noise ratio, probability of detection is clearly equal to probability of false alarm. That means we cannot basically detect any signal. So let us consider these two axes, where the x-axis corresponds to the values of probability of false alarm between value 0 and value 1, and the y-axis corresponds to probability of detection with values from 0 to 1. And for s equal to 0, the ROC curve should look like this. That is, it is basically a straight line where probability of detection is equal to probability of false alarm, and the slope of this line is clearly equal to 1. Basically, this is the worst ROC curve we can have. Next, as the value of SNR increases, that is, SNR increases, then basically the curvature of ROC changes. That is, SNR is greater than 0. And we can clearly see that this is a non-decreasing function. And as the SNR becomes very large, the ROC curve will look something like this. That is, the probability of detection will get closer and closer to 1 even for lower values of probability of false alarm. And of course, at infinite SNR, we'll have a straight line. That is, probability of detection is equal to 1 for s equal to infinity for all values of probability of false alarm. So, in other words, the probability of detection will approach 1 as signal to noise ratio increases even for smaller values of probability of false alarm. Now let us look at the dependence of ROC curve on the threshold gamma. So dependence on the threshold or detection threshold. So by definition, probability of false alarm is equal to Q of gamma dash over square root of sigma square by n, which is equal to integral gamma dash over sigma square by n, that is square root of sigma square by n, to infinity of the probability that the test statistic t of x is greater than gamma dash under null hypothesis h naught. And clearly at value gamma dash equal to minus infinity, that is, when the first limit is equal to minus infinity, then probability of false alarm is equal to integral minus infinity to plus infinity of a probability distribution of t of x greater than gamma dash. That is, t of x is greater than minus infinity under null hypothesis. This integral is clearly equal to 1. Therefore, the probability of false alarm at gamma dash equal to minus infinity is clearly equal to 1. And similarly, the probability of detection, which is also equal to Q function of gamma dash minus a over square root of sigma square by n. And at gamma dash equal to minus infinity, that is, probability of detection at gamma dash equal to minus infinity is clearly equal to the Q function at minus infinity, which is equal to again 1. And similarly, for gamma dash equal to plus infinity, the probability of false alarm at this value is equal to the Q function at plus infinity, which is clearly equal to 0, since both the limits of the integral are same and the integral is obviously equal to 0. And similarly, probability of detection at gamma dash equal to plus infinity is equal to Q function at plus infinity, which is also 0. Therefore, the ROC curve has the following dependence on the threshold gamma dash. For gamma dash equal to plus infinity, we have the probability of detection and probability of false alarm equal to 0. And for gamma dash equal to minus infinity, we have probability of detection and probability of false alarm equal to 1. And for all the other values of gamma dash, that is, as gamma dash increases, we basically come down the ROC curve from probability of detection equal to 1 to probability of detection equal to 0. That is, gamma dash increases in this direction. So, from these two dependencies and the definitions of probability of detection and probability of false alarm, we can clearly see that both probability of detection and probability of false alarm, both the values are clearly non-increasing functions. With respect to gamma dash. Thanks for watching.